The extreme value theorem is saying this: if f is continuous, it is continuous on a closed, interval. So suppose I have an interval a, this is a, up to b, and then of course if you look carefully into this, we're actually having this. So then first, the function is continuous. If the function is continuous, it must be defined at a point, and also at the same time the limit from the left and the limit on the right must exist, and it must also be equal to the value of the function. That was the meaning of continuity. So if, let's say, we have a function that is continuous on this interval, right, then f attains an absolute maximum. Absolute maximum value f of c, and an absolute minimum value f of c. No, this one is not going to be c again, d, unless they are equal, at some point c and d in a and b. So basically what the extreme value theorem is saying, that if you are actually having a continuous function can actually be something of that sort, and then you are looking for the highest possible value this function can actually have. Its output of the absolute maximum must be an output of a value that is between these 2 points, or the image of some value that is between these 2 points. Let me make a simple example here by drawing. Why am I having weird drawings here? So suppose I have a nice drawing like this. I have the x and y plane, and then I also have another one here. I'm going to try and make as many examples as possible so that you can actually see. And then I can also have another one here. And then I can also have another one there. I'm just gonna place maybe 2 here, just 2. I have this one, and also I'm gonna have this one here. So basically I am having y, I have an x there, I have a y, I have an x, I have a y, and then I have an x, I have a y, and then I have an x there, I have a y, and then I have an x. I'll try and explain here. So if, let's say, you are having a function of this type here, right? So I'm having a function here, and this starting point here is a, and you can see that this point is defined, and that point is also defined there, and then it is an output of b. So if you are looking for the maximum value of this function, you can see that this point here is the largest value this function can actually have. Remember that the extreme value theorem is only talking about the absolute maximum and the absolute minimum. That is all, nothing else. So the maximum value here is going to be here. This is the maximum value. This one is the absolute maximum. So we have an absolute maximum. Yes, of course, at this point, because whenever I'm picking up points that are in between, that are close to this, they are less than this, so it is also a a local maximum, but the extreme value theorem is only talking about the absolute maximum and absolute mean. So this one here is the absolute maximum. So since this one here is an absolute maximum, you can see that this point is on this function f, and it is this point here, we can say that it is f of, and then here we are actually having a c, so it is f of c. So this value c here is a value that is in between a and b. That is what the absolute the extreme value theorem is saying, is that if you look at the absolute maximum, it is an output of some value that is in between these 2 points. And then another one, you can say that if, let's say, you are actually having a graph of this type, and of course this is going to be a, and this one here is going to be a b, you can see that the absolute maximum will be there, and it is an output of some c that is there. So this c is in between these 2 points. That is what the extreme value theorem is saying. Another one will be something of this type, and we're having a graph that is actually doing something of this kind here, and this point here, which is the starting point, is going to be a, and the ending point, we call it a b. So if you look at this point here, actually this one is less than that, so this one is just a local maximum, but this one is an extreme maximum, or it is an absolute maximum. So hence we are saying this is an extreme value theorem. It's talking about the extreme maximum or extreme minimum. You get what I mean? And the extreme minimum is talking about the absolute. So here, if you look into this point, this is the highest point. This is the highest, but it's not higher than this. So this one is actually the absolute maximum. So if you are having this extreme maximum that is here, look at its input value. Its input value is going to be somewhere here. So you are actually having a c there. So this c here, it is a value between a and b. And if you are looking at this point here, you can see that this point is actually less than this point, and also less than that point, and also less than any point that is here. So this one is an absolute minimum. So this absolute minimum, it is an output of a point D here, and this point D is still between A and B. That is what the extreme value theorem is actually saying. And now, if let's say I'm having a graph of this type here, and this graph is actually, I'm having a point, let's say here, this is 0, we know, and then I'm having a point, let's say 2 there, and I have a vertical asymptote there, and this function is growing all the way up. So this function is not going to touch at this point, so it keeps increasing all the way to infinity. So if you look at this point here, this point is supposed to be the lowest value this function can have, this function f can have. So it's supposed to be the lowest. But now at this point, this function is not defined. So if you look into this point here, or this function here, you will find out actually this function here is not defined. So when you're picking a point so close to it, it's because you can't really pick a point that is so close to this point. We don't know what is that value there, because if let's say this is 0, maybe I'm gonna say the value so close to 0 is 0,0000001. The question is, how many zeros should I place so that I get the last point that is so close here? I don't know what is exact that value. So this function here, we usually say that it does not have an absolute. It does not have an absolute minimum, or the absolute minimum does not exist. Absolute minimum is the same as global minimum, so it does not exist because of that point. And if you go close to this point, the maximum value this function will actually get is somewhere at infinity. So because this function, we cannot pick that point and say this is our maximum value, so we also say that this function does not have an absolute maximum. So a function of this type does not have both the absolute maximum and the absolute minimum, because here is not defined, but this one keeps growing unboundedly, so we actually don't have a maximum there. So does not have an absolute maximum and does not have an absolute maximum. So we don't have an absolute maximum, we don't have an absolute minimum, because here is not defined, and also at that point it is actually growing unboundedly. If you look in our previous lecture, you will find out that here, as much as this function is not defined here, it was not that. This one was not defined, but this one was defined. In this case, we actually had an absolute because it was defined at that particular point. So that what was actually nice. Let's take another example here. Another example is going to be something nice like this. Now it is defined, and then I am actually going all the way up, and then here I'm gonna say it is not defined, but I want this function to be defined somewhere here, and then I'm gonna go all the way and then hit a point here. So what is actually happening here? You can see that this point is actually smaller if you are considering this part, but this point has nothing on the left, so it cannot be the local minimum. And also at the same time, this point is bigger than these points here, so it cannot be an absolute minimum. But this one here is the lowest there is. So if you look here, let's say it was a 2, you look at f of 2. F of 2 is equal to 0, and this one is the absolute minimum. So it is absolute minimum. So it is the lowest value this function can actually have. But if you look at some point here, I'm going to call it A, and you go all the way up to here, this function is defined at this point, but this point that is here is above this point, so we cannot say this is a maximum because there is a point that is larger than it. And if I pick a point here, it's still larger than other points that are there, but at this point it is not defined, so I should be picking a point somewhere here that is the maximum or the highest, but I can't really pick that point because there are so many numbers between this line and that line and that line and that line, so there are so many numbers that are here. This interval is so dense with numbers, so in this particular case here we actually don't have an absolute maximum because the absolute maximum is actually sitting somewhere there. And also at the same time, if let's say you wanted to talk about the local maximum here, you will find out that first of all the function need to be defined at that point, but the point whereby it is defined is somewhere here. So the points that are there are bigger than this, which are close to this, so we don't have a local maximum. We also don't have an absolute maximum. I hope you actually understand this whole thing here, because that is actually what is actually important here. Now that we actually have this, I want us to talk about the Fermat's theorem. What does the Fermat's theorem is actually saying? Is saying that if a function f has a local, so it must have a local maximum, or it must have a local minimum at some point C, right? And f prime of C exists, then f prime of C must be equal to 0. I know that we have been using this for a while, and most people, they think that once I end up having a derivative equal to 0, at that point we must actually end up having a derivative. We must actually end up having a turning point. That is what we were doing in high school, and there's nothing wrong with that, because at that moment the only information we could give was the information I gave you. It's not saying that what we told you was wrong. We are expanding from that now. If we have a function f has a local maximum or a local minimum at some point C, and we know that the first derivative at that point exists, then the first derivative must be equal to a 0. So if I give you a function and you find its derivative, right, and its derivative, you find out that there is some point whereby the derivative is equal to 0, then either the function is actually having a turning point at that point, or it does not have, even though we know that the derivative is equal to a 0. The second thing is saying this: if let's say you are finding the first derivative and you set it equal to 0, you get some values there. It does not mean that the function has a local maximum, a local minimum, or a turning point or not a turning point. What this thing is only saying is that first, the function must have a local maximum or must have a local minimum at that point. Secondly, the derivative must exist. So those two conditions must exist. Then we will say that the derivative must be equal to 0. This is one of the theorem that we have actually been using throughout. For instance, here, suppose I am giving you a function. I'm saying that we have f of x is equal to I'm gonna end up having x squared, and then I'm gonna say minus 2x, and then I'm gonna end up saying here I have a plus 1. So if you look into this function here, first of all, it must have a turning point, right? This function does have a turning point, right? So if I were to draw this function, I know for a fact that what is important with this function, because this is actually positive. So if I were to draw this function, it will actually look something like, because it will actually look like something that is concave up. And also, of course, we have a plus 1. So this function will actually look something like this. So first of all, I know that there is some turning point somewhere there. And then secondly, does the first derivative exist at some point? So if I take the first derivative of this function, I will get 2x minus a 2, and then if I set this equal to 0, it means that I have 2x minus 2 is equal to 0, or 2x is equal to 2, or x is equal to 2 divided by 2, 1. And then of course, if I take this and plug it in that function, I will end up having f of 1, which is just 1 squared, which is 1, minus 2 times 1, which is 1, plus 1. So basically, I will end up having 1 minus 2 is going to minus 1, plus 1 is going to be a 0. So we know that there is a turning point at that when x is equal to 1. So this function was actually supposed to look like something of this type here. We're supposed to end up having this, and we have the Cartesian plane. When x is equal to 1, we have a turning point, right? And then we know that when I'm plugging it there, we're getting a 0. So we're actually having something of that type there. When x is equal to 1. Did I do something wrong here? Because this is the same as x minus 1 squared. Yes, we have something like that. So this function was supposed to look something like that. So if you can see, first of all, we wanted the local maximum or local mean. So we're actually having a local mean there. And so the first condition is satisfied. The second condition is we actually want the first derivative to exist. So this derivative here exists everywhere because the domain of this function is a set of all real numbers. So that condition is also satisfied. And now, if let's say we're taking we're plugging in this one here in this particular function, we know that if let's say I were to take x is equal to 1 and plug it here, I will get 2 minus 2, which is just a 0. That is what this thing is actually saying. I hope you can actually get this, because this is not about the output of the function, which is actually that I was doing this to actually plot this whole function the correct way. This has to do with the fact that if I plug in x is equal to 1 in this function, I'll end up getting a 0. So the first derivative is equal to a 0. And then the second thing that I want you to actually pay attention to now is this. If let's say I ended up saying I have f of x is equal to x to the power 3, or I have f of x is equal to the absolute value of x. If you look into this function and you want to actually end up plotting it, so this function will actually look something of this type. So this function will actually look something like this, and then it goes there, and then it goes all the way like that. And then if you are plotting this function this side, this is y, this is x, this is y, this x. This function will look something like this, and then this side it will look something like that. Of course, this is f. So what is actually happening with that function? If let's say I were to take the first derivative of x with respect to x, I would end up getting 3x squared. And if you look at I'm setting this equal to 0, you will find out that I will end up getting 3x squared equal to 0, or divide on both sides by 3, I will get x squared equal to 0, which means that x is just equal to 0. What that's supposed to mean here, it means that when I'm looking at f prime of 0, I actually get a 0. So looking into this function here, what I'm actually having here, I am actually having the first derivative is there, and then secondly, I know that this one here have a domain of x is an element of real numbers. In other words, the derivative exists everywhere for this particular function. And if I'm taking 0 and I'm plugging it in this derivative, I get a 0. Now, let's go back and look at what Fermat's theorem is saying. It is actually saying first there must be a local maximum or a local minimum. And it does not say that at this point here, if this one exists, then there must be a local maximum at that point. That is not what it is saying. Because looking into this function here, this function is increasing throughout and is increasing throughout. If let's say I pick this point here, when I pick a point on the left of 0, it is less than that point. When I pick a point on the right of 0, it is actually bigger than that point. So this point here is not a local maximum or minimum, because this function is increasing throughout. Just because you are having a derivative equal to 0, it does not mean that there is a turning point at that point. I hope that's you are actually getting that, because at some point you will actually find out that most people wanted to say that if the derivative is equal to 0, therefore this must happen. That is actually not the case. And also, if you look into this particular function here, you will find out that we did the derivative of that function, and we know that when you actually look into this function here, we are actually having, at this point, if I pick this point here, we are actually having a local, not only a local, actually we have here we're actually having a local minimum, and we are also having an absolute minimum. But when you look at f prime of 0, you know that f prime of 0 does not exist. So this one does not exist at all. So when we were using the first principle, you saw that the derivative of this, what was the derivative of this? And it does not exist at that particular point, because when x is less than 0, this function is decreasing, and it was decreasing at a constant. So we know that f prime of x was actually something of this type. It was -1 if x is less than 0, and then when it came to x greater than 0, it was actually 1. And when we are evaluating what was happening at 0, we find out that this one does not exist. So that is why we're saying it does not exist, but there is a local mean. So what this is saying, the function can end up not having end up not having a local from this. The function can end up not having a local maximum or local minimum, but the derivative exists. And secondly, the function can actually end up having a local minimum, right? But the derivative does not exist. So Fermat's theorem is actually specific that what we want to happen, we wanted the function to actually end up having a local maximum or a local minimum, like this case here. And secondly, we wanted the derivative to exist everywhere. This was actually, where's this? This was actually the derivative. It actually existed. And then after it existed, that's when you can conclude that there is some point, which is in this case x1, such that if you are plugging it in the derivative, you are getting a 0. That's what this Fermat's theorem is actually saying. I hope you can actually understand what it is saying and end up removing that mindset that whenever you're having a derivative equal to 0, then there's a turning point, or whenever there is a turning point, the derivative must be equal to 0. The modulus function is an example whereby you are having a turning point, but the derivative is actually not equal to a 0. Let's talk now about the critical number. I want us to give an a definition of that. Definition. So what do we actually call a critical number? A critical number. A critical number of a function f is a real number c on the, not on, supposed to be in the domain of f. So it is in the domain of f such that we have either f prime of c is equal to 0 or f prime of c is undefined or does not exist. Right. So a critical number is just that number, right? So what we're actually saying here, if f has a local maximum or minimum at c, then c is a critical number. That's what is important here. So basically, if you're actually looking for a critical number of a function f, you just take the first derivative of this and then you set it equal to 0 and then you solve for x. So all the x values that are making the first derivative equal to 0 or undefined, those are the values that we call the critical numbers. Again, I said that you take the first derivative of the function and then you set it equal to 0. So all the values that are making the first derivative equal to 0 or making it undefined are the values that we're actually making. We are saying they are actually critical numbers. So let me write this thing down so that you have some reference. Suppose first I'm going to talk about the closed interval method. So these ones we're actually talking about the critical number. I told you how to find the critical number, that you first find the first derivative, secondly set it equal to 0, and then you find those values that are making it equal to 0, and then after that you also check the values that are making it undefined. The values that you are getting, they are actually the critical numbers. In other words, they are actually the x values. The absolute max, the absolute mean, the local mean, and the local max, those are talking about the outputs. So critical number and those extremas, they are kind of little bit different, because critical number is talking about inputs, and global max and global mean and local mean and max, they are actually talking about their outputs. So to find the absolute maximum or global maximum, or absolute minimum. Remember that absolute minimum is the same as global minimum. Absolute minimum values of a continuous function. Of a continuous function on a closed interval. Let's say this interval is AB. How do you end up finding the absolute maximum or the absolute minimum of a continuous function? Remember that what I'm going to tell you is only applicable to continuous functions on that particular interval. But if it's not continuous, then you will have to find a way. Of course, you will never be asked to find things that are not continuous. If I only taught you things that are based on continuous functions. So the first thing that you need to do to find the absolute max or the absolute mean, first thing is find the output of f at the critical numbers of f on the interval on the open interval AB. So first of all, you first find the critical numbers and then you plug them in the function, and then you see what you are actually doing here. So basically, this is usually confusing sometimes, but once you get used to it, it's going to be easy. First, you find the derivative of this function f, and then you find the values of x that are making it the first derivative equal to 0. And then after that, you get those x values. You, out of all the x values that you are getting, you check the values that are still in between a and b, and then you take those values, you plug in this function, not the first derivative, this function, and see what you are actually getting. And then those outputs are what we are talking about here. And then once you have those outputs, right, you find, this is number 2, find the output of f at the end points. That is what I actually want you to find here. That is, you actually find what is f of a and what is f of b if we are talking about this interval a and b. So you want f of a and f of b. And then once you actually end up finding those things, you will actually so close to actually end up finishing this whole thing, because what you need to do now, you just have to compare this one with that one and also the outputs of the critical numbers that you got here. So the largest of the values from step 1 and 2 is the absolute maximum. So it is an absolute maximum, and the smallest value. So here's the smallest value from step 1 and 2 is the absolute minimum. So that is actually what is important here. And then of course you will find out that this is the easiest thing that you actually end up having to do here. You first find the first derivative, you find the x values that are actually making it equal to 0 and then or undefined, and then you take those values, you plug it in the original function, and then once you plug them in the original function, you check the outputs of the endpoints with those outputs of the critical numbers, and then after that the largest value, or the value that is larger than all of them, is the one that you call it an absolute max. Sometimes it does not exist, so don't always expect it's going to exist. And then secondly, the smallest of them all is going to be the absolute max. So that is actually what is actually important in this. And of course, if let's say I were to give you a function and say, I'm just going to give you one example here. The example would be find let me put it like this. Suppose f of x is equal to, I'm going to say here we have 2x squared plus 4x minus, let's say maybe 15. Or should we use, let me use this function here. And then I have this. And then we have this one. And then the question is saying here, I'm going to place an A here. Find the absolute maximum, or someone might say find the global maximum of f on the interval. I'm gonna put it here 5 minus 5 and 5. The second question is going to say find or evaluate or calculate the absolute minimum, or someone might say the global minimum of f on the interval minus 5 and a 5. Now, if you look into this, because this is an example that I just thought of, so I want us to actually end up finding a solution to it. So what was the first step? Solution. So the first step is saying this. First, we wanted to find the critical numbers. In other words, we want to find the first derivative. So I actually I still have f of x is equal to 2x squared, 2x squared plus 4x minus 15. So that is actually the function. So the step one is we wanted to find the critical numbers and their output. So you first find the first derivative with respect to x of this function, and then when you're finding the first derivative, you will end up having 4x. 2 times 2 is 4, and then plus, and then here we'll end up having a 4. Of course, the derivative of this 4 and the derivative of that is 0. And then what we do after this, we just say that we wanted to set this equal to 0, so we'll end up having 4x plus a 4, and then we set it equal to 0, and then we solve for x. So this one is just saying I'm going to take this to the other side. Okay, let me just write here. We'll have 4x, this was positive, so on the other side is going to be negative, and then I divide by 4 on both sides. this 4 is this one. Therefore, I can say that our x is equal to minus 1. So x is equal to 1 is one of the critical numbers. So the next thing that I wanted to do here, I wanted to find f of minus 1. So I'm going to plug in the original function, not the derivative. So I'm going to plug it here. So I will end up having 2, and then I will have minus 1, and then I'm going to square it up, plus 4, and then I'm going to plug in minus 1, and then I'm going to subtract a 15. So what is the output that I'm going to get? I will have a 2, and then I'll have a minus 1, and then of course I want to square it up, and then a plus 4, and then I have minus 1 inside, and then I want to end up having a minus 15. Hopefully these numbers are actually making sense. So I have minus 17. So basically now this is the output of the critical number. This one is the critical number of f. Now I have this. So the next thing that I need to do now, I need to look what is the output of this and what is the output of that. So if I look into this, I want to end up having f of minus 5, and I want to end up having f of 5. So what are these values? Right. And then I am going to end up plugging here a minus 5, and then here I will end up plugging again a minus a 5. So this answer here, the answer is 15. And then if you look into this one now, I wanted to use a positive 5, and then here I want to use a positive 5, and here I am having a 55. Right. What is step 2? Step 1, we wanted to find out the critical numbers. What is this? Step 1 wanted to find the critical numbers of that on the open interval. We got it. Find the output at the end points and find f of a, and that we did that. Now we are looking at the largest value. So if you look here, we are actually having f of minus 1, and f of minus 1 is minus 17. So this one is equal to minus 17. And if you look at minus 17 is less than 15, and 15 is equal to f of minus 5. And if you look at 15 here, it is also less than 55, and 55 is the same as f of 5. So now the last question is saying this. What is the, if you look at A, what is A saying? A is saying they want us to find the absolute maximum. So f of 5, which is equal to 55, is the absolute maximum because it is the largest value that is maximum. And then if you look at B now, this one is the smallest. So f of minus 1, which is equal to minus 17, is the absolute minimum. So that is actually what is important when it comes to this. I hope you actually understood this, because we are actually going to end here for this particular lesson. So we're going to end there. We talked about the absolute and the extreme value theorem, and then we talked about Fermat's theorem, and we talked about the local extremum, the local extremum, the local minimum. I mean the local extremums, we talked about them, and we also talked about the absolute maximum, the absolute minimum, which is, and also talk about the global minimum and stuff. So we talked about those things. So I hope you got a little bit of an idea there. And then next time we will talk about what is called the mean value theorem. And basically the mean value theorem is the one that is actually giving clarity on, if let's say you have a function that is actually increasing on this particular interval, then the output on each interval, can we compare them, yes or not? So it is that theorem that is actually giving us clarity on that. So let's just end there and hope you can digest this whole thing and see what is actually happening.